Let's start with the basics of just trying to keep track of what time it actually is. There's some terminology we'll build up, and then we can explain some of the issues. The first term is local time. That's the time based on the local microcontroller clock rate. So your microcontroller has an oscillator that might be at 8 megahertz or 32 megahertz or whatever, some number, and it oscillates back and forth. But every oscillator in every microcomputer has a slightly different rate. And so there's a local time based on that clock rate. Generally, every so many clock oscillations or CPU cycles, there's a timer interrupt, and then there's software that keeps track of the time from there. I said the oscillator is not perfect, so there's a local time, which is the time your system thinks it is, and there's a drift rate, which is how different your local passage of time speed is versus a perfect clock. For example, 0.002% is 0.00002 seconds per second drift rate. That means that every second that passes, you might be 0.00002 seconds wrong. That's not a lot of time in 1 second, but there's a whole lot of seconds in a year. This is actually a somewhat common type of drift rate at that rate, and at the end of the year, you can have several minutes of inaccuracy in your clock. Now, what do I mean by accuracy? Accuracy is the local clock versus perfect time. For example, if you have a multi-node system, node number 2 is 1 second slower than true time, and so its accuracy is off by 1 second. Every local clock has a different accuracy, but all those accuracies are with respect to whether or not it's on top of a universal notional perfect time or whether it's off. It's common for embedded systems to have multiple computers coordinating, not necessarily even in the same time zone. And so the time difference between two clocks is the offset. So for example, node 1 may be 3 seconds faster than node number 3. This offset has no idea what accuracy. Both clocks could be an hour off from perfect time or 10 hours off from perfect time, but as long as the two clocks agree within 3 seconds, maybe that's good enough for your application because you're interested in agreement rather than running a clock display. Every pair of local clocks within a system has an offset. Well, that sounds like it could be kind of chaotic if the offsets are completely random, and so there's the notion of precision. Precision is the maximum offset between any two local clocks. And so if number 3 node is the slowest in the system and number 1 node is the fastest in the system, the precision is their offset, which is 3 seconds. There's only one precision value for a system because it's a global across the system kind of number, whereas every pair has an offset. The notion of precision and accuracy are decoupled. Again, precision has to do with whether or not all the clocks in a particular embedded system agree with each other, and accuracy has to do whether that agreed upon value is actually representative of actual universal notional perfect time.